Okay, good. Good afternoon, everyone. I am Wenchano. So I'm going to talk about an efficient approximation algorithm for the online multi-tier, multi-cell user association. I'll start with the motivation. So we know that wireless bandwidth demand is pushing cellular networks to multi-tier architectures. It may consist of macro cells and a bunch of small cells. So under this architecture, the user base station association problem is critical to the overall network performance. So, however, previous analytical work is focused on the offline and static user base station association, where users' arrivals and their race are assumed to be known in advance. On the other hand, practical online algorithms is often based on heuristics, which may not provide any performance guarantee. So our contribution is to propose an online algorithm for the multi-tier user base station association problem that has a provable performance guarantee. So the online algorithm is motivated by online combinatorial options. It also captures and leverages the relative sparsity of choices in wireless network. So specifically, it is a 1/2 minus alpha to the -1 approximation algorithm, where alpha is the maximum number of feasible associations for a user and is generally small due to path loss and interference in wireless medium. So this bound is the tightest bound up to date. Here is the outline of my talk. So first I will introduce the system model and then introduce the offline setting. And then for the online algorithm, there are totally 3 algorithms. The first one is called user-centric, and the second one is CELL-CENTRIC deterministic online algorithm, and the third one is a CELL-CENTRIC randomized online algorithm. And for the performance analysis, I will discuss the performance bound for the 2 CELL-CENTRIc algorithms. After that, I will discuss some simulation results. So here is the system model. We consider a multi-tier, multi-cell network. So in the cartoon, there are 2 tiers. So we can think of it as a macro cell and some small cells. So the users' arrival, we assume that the users arrive online one by one. And each user shall be associated upon arrival to one of the base stations. And the association decision is immediately and irrevocably made based only on the past user arrival profile. Yes, so this is the setup. And then here are some notation. We use U to denote the set of users. So there are total M users. User 1 arrives first to the system, and user M arrives last. We assume that there are a total number of K tiers, and we use capital K to denote the set of tiers. In each tier, we assume that there are NK base stations, and we use the set BK to denote the set of base stations at tier K. As a result, we can see that each base station is indexed by a tuple JK. We call it base station J at tier K. So we also define the set AI, which is the set of base stations that user I can potentially be associated with. So we can see that AI is the set of base stations where the received signal to interference and noise ratio at user I from the base station JK is larger than or equal to some threshold tau. So the tau is chosen to ensure that the data message can be decoded successfully at the receiver I. So last, the data rate between user I and base station J at tier k is denoted by Cijk. So where we use the Shannon formula for the data ring. All right, so let's move on to the offline setting first. So in general, we are consider network utility maximization problem. We maximize some utilities of users. So for user I, we use UI to represent its utility. Yes, UI is here. Okay. And then the optimization variable or the decision variable is Xijk. So Xijk equals 1 if user I is associated with base station J at tier k. So when there are multiple users associated with the same base stations, we assume that equal time sharing is used to schedule the users for their transmission. So we can see that the utility function of user I, UI depends on the effective data rate. So the effective data rate is just Cij divided by the time sharing fraction. So the first constraint is that each user can only be associated with one base stations. Last, the optimum offline utility. We use OPT to denote the optimum offline utility. So here is the first online algorithm. We call it user-centric online algorithm. So the general idea is that when a user arrives, the user is associated with the base station that maximizes the user's own utility. So this is, we can see that it chooses the base stations JK belongs to its potential candidate set AI that maximizes the utility of user I, UI, right? So the variable SJK updates the number of users currently associated with base station JK. So actually, it is the system load of base station J at tier K. Right, it's quite trivial, straightforward. So the resulting sum utility of this algorithm, we use ALG user to represent it. So before we move on to the CELL-centric algorithms, we first introduce some definitions. So AJK is the set of users that base station J at tier K can be associated with. Yeah, we can see that it is the counterpart definition of AI. Yeah. So VJK is the utility of base station J at tier K. The utility of base station is defined as the sum utility of its associated users. We can see that the domain of this function is defined on AJK, and S is any subset of AJK. So last, we use the VJK I/S to denote the marginal utility of base station JK for associated with a new user I, given the current set of association S. Yes, you can see that the marginal is defined by the last formula is VJK S union the new user I minus the VJK of the current set of users S. Okay, so after this definition, we will introduce the first CELL-centric deterministic online algorithm. So the general idea is that when a user arrives, the user is associated with the base station that has the highest marginal utility of that particular user. So we remember that the user-centric is to associate it to the base station that gives the highest user utility. But in this CELL-centric, the user is associated with the base station that gives the highest marginal utility. Right, so similarly, the SJK updates the current set of users that base station JK is currently associated with. So we use ALG cell to denote the resulting sum utility of this algorithm. So here is the third one. We call it CELL-CENTRIC randomized or Nye algorithm. So the general idea is that when a user arrives, the user is associated with a base station in a probabilistic manner. So the probability is proportional to the base station's marginal utility of including that user. We circle the probability. So we can see that the higher the marginal utility, the higher the probability of association the user I to that particular base station. So since this is probabilistic, so we call it a randomized or Nye algorithm. And similarly, as JK updates the set of users that base station J at tier K is currently associated with. And also the resulting sum utility is denoted as ALG cell rep. So before performance analysis, we have two definitions. The first is that the base station utility function is submodular if the marginal is decreasing. And the second one is that we call the utility function, the base station utility function is monotone if the marginal is greater than or equal to 0. So we give an example. So we use for example, we use the logarithmic user utility, which corresponds to the notion of proportional fairness. So under this logarithmic user utility, the base station utility function becomes the following, becomes the first equation. So by using some basic analysis, we can show that this particular form of base station utility function is submodular and under mild data rate constraints, which can be easily satisfied in any real-world scenarios. This base station utility function can be shown to be monotone, and the details are provided in the paper. So with these two results, we have some theory. So the first one is for the deterministic algorithm. So we can show that under the submodularity and monotonicity, we can show that the CELL-centric deterministic algorithm achieved an utility greater than half of the OPT, half of the offline optimum. And the CELL-centric randomized algorithms, so similarly, under the submodularity and monotonicity, it achieved an average utility, which is greater than or equal to 1/2 minus a to the minus 1 of the offline optimum. So this alpha or small a is the maximum number of associations of a user, so which is typically small, say 2, 3, or 4 for any reasonable topology due to the path loss and interference in the wireless medium. So the general proof idea is motivated by online combinatorial options, and where we use induction on the number of users and some inequality, such as the AMGM inequality. So the details are in the paper. So here are some simulation results. So we first consider a two-tier heterogeneous network. So we can see on the cartoon on the right-hand side, we use the blue square to represent the macro base stations, and the red circle to represent the femto base stations, and the black dots to represent the users. So we can see that the users are distributed in a non-uniform manner. So in each interlacing squares, some squares have a higher density of users and others has lower densities. So under this particular topology, we we can see, we show that most of the realization of this topology has alpha equals 3, means that a user can only be associated with at most 3 macro or femto-based stations. Yeah. We note that this particular value alpha depends on the path loss topology and the decoding threshold. So we compare 4 schemes: the randomized cell-centric scheme, the deterministic cell-centric scheme, we use cell to denote that, and a user-centric scheme, and a mixed SINR scheme. So in the mixed SINR scheme, a user just associate with the base station that give his highest SINR value independent of the system load of that particular base station. So it just connects to the base station that gives the highest SINR, ignoring the load of that base station. So there are 4 matrices. The first matrix is the sum log rate. It's just the sum utility of our optimization problem. So this sum log rate corresponds to the notion of proportional fairness. So we also compare the minimum user rate and also the James fairness index. So the James fair index is between 0 and 1. So the higher, the more fair. So 1 is the largest. And also the last matrix is the sum rate. So we can see that the 4 matrices corresponds to the cartoon A, B, C, and D. And then the 4 bars are for the 4 algorithms: the cell randomized, the cell deterministic, the user, and the mixed SINR. So we can see that both cell-centric algorithms performs better than the mixed SINR for the sum utility, sum log rate utility, for the minimum user rate at figure B, for the James fairness index. But on the other hand, the mixed SINR can give a higher sum rate since it ignores the fairness among the users. So we can see that in figure D, the mixed SINR give a higher sum rate than the other 3 algorithms. All right, so here is a different topology. In this topology, the users are homogeneously distributed in the areas. So we can observe similar trends as the previous one. So here we consider a multi-channel Wi-Fi network. So there are total about 20 access points, and each of them operates at one of the 4 channels. We use different color to represent different channels. So in this multi-channel Wi-Fi network, the users are concentrated at the center. And we can show that most of the realization of this topology has the alpha value equals 4. So the maximum number of potential association of a user is 4. So we can see that in this particular topology, the cell-centric outperform the others in all 4 matrices. So the last one is the same as the third one, except the users are homogeneously distributed. So in this case, since the users are already distributed in an even manner, so they already balance out with each other. So we can see that all the 4 schemes give similar performance in terms of the 4 matrices. So here is the conclusion. So in this work, propose a 1/2 minus alpha to the -1 approximation algorithm for the online multi-tier user base station association problem, which is the tightest bound up to date. And alpha is the maximum number of potential associations for user. and it is small due to path loss and interference in the wireless medium. Also, through the simulation results, we can see that under realistic scenarios, the proposed algorithm performs, the proposed online algorithm performs nearly optimum and has the desirable fairness properties. Yeah. So that's it. Thank you for your listening.